A very nice welcome to the भारतीय फार्मर क्वांटम फिजिसिस्ट क्लासेस और कृषक भारतीय कृषक और भारतीय किसान क्वांटम कृषक classes. And in the previous lecture we calculated the phase velocity of the which is given by v sub p equals to c square by v. This is equation 8. And from this we see that since v is very less than c, the phase velocity of waves associated with matter comes out to be greater than the velocity of light. Does this disturb you? So here, do not worry, because no physical quantities like signal energy or information associated with the wave travels with its phase velocity. Equation 8 is a complete statement. Equation 8 is a complete statement of the wave particle duality. It clearly shows that a particle with a momentum p can exhibit wave-like properties, and the wavelength of the associated matter wave is h by p. The converse is also true. That is, a wave of wavelength lambda can exhibit particle-like properties, and the momentum of wave matter is h by lambda. But we should understand the difference between electromagnetic waves and matter waves. For matter waves, phase velocity is always greater than the velocity of light, but since energy is carried by the particle, the velocity with which energy is transported by matter wave is equal to the velocity of the particle. On the other hand, the phase velocity of electromagnetic waves and the velocity with which energy is transported by them are both equal to the velocity of light. If matter can exhibit wave-like properties, why don't macroscopic objects appear like a wave to us? Let's clear this with a calculation. Consider a ball of mass 10 to the power minus 3 kg moves with a velocity of 10 to the power minus 2 meter per second. So what is the de Broglie wavelength of this ball? Here is the calculation given. We know that matter waves wavelength for matter waves lambda equals to h by p, and using given value we get it comes out to be 6.626 into 10 to the power minus 29 meter. Clearly this wavelength is very small to be detected experimentally. Hence, we can say that matter waves are associated with macroscopic objects. However, their wave character is not observable. Thus, they can be described as particles under all circumstances. Now, let's see another example. For example, we calculate the de Broglie wavelength of a 100 electron volt electron and a 1 mega electron volt neutron using the above formula. So here is the calculation for electron, that is wavelength of electron, lambda sub e equals to h by under root 2 m naught e, and using all value we calculated its value, which comes out to be 1.227 to 10 to the power minus 10 meter. Again for electron, this calculation is lambda sub n given by this relation, above relation, and using the given value we get the value of lambda sub n, that is wavelength of neutron, which comes out to be 2.862 into 10 to the power minus 14 meter. So here we have calculated the wavelength to be about 1.2 into 10 to the power minus 10 meter for 100 electron volt electron, and 2.9 into 10 to the power minus 14 meter for the 1 mega electron volt neutron respectively. Clearly the wavelength of the matter wave associated with 100 electron volt electrons lies in the X-ray region and is of the same order as the atomic spacing in a crystal. The electron wave, like X-ray, are therefore expected to undergo diffraction by crystal. On the other hand, the wavelength of a 1 mega electron volt neutron is too small. 1 mega electron volt neutron is too small to observe the diffraction by a diffracting grating. However, low energy neutrons, say 100 electron volt neutrons, would have wavelength in the X-ray region, and then their diffraction pattern can be obtained. Thus, we see that for the motion of macroscopic object, the de Broglie hypothesis does not change the classical description as observed as developed by the Newton. But for microscopic object, the wavelength of matter waves are long enough to undergo observable diffraction. The diffraction of matter waves was observed experimentally in 1927. So now we see the experimental proof for the existence of matter waves. The first experimental proof or demonstration of matter waves came 3 years after de Broglie advanced his hypothesis and was accidentally obtained by two American physicists, Clinton J. Davison and his assistant G. H. Jarmer. They were studying the scattering of electrons by crystals using the apparatus as shown in figure. Electrons from electron gun were accelerated by a positive electrode maintain and V volt as compared to the filament. The accelerated beam of electrons was incident on a strip of nickel containing many crystals, and the number of electrons scattered in various directions was then measured. A smooth variation in the intensity of the scattered electron with the angle was observed. Midway through the experiment, an accident occurred which gave air to enter into the vacuum tube containing the strip. This resulted in the formation of an oxide film on the surface. Davison and Jarmer were then forced to heat the strip to a very high temperature in order to reduce the oxide, This heating and slow cooling had the effect of turning the polycrystalline nickel sample into a large single crystal. After this forced heat treatment of the sample, the experiment was repeated. The experimental results this time were quite different from those obtained from the before the accident. The intensity of scattered electrons shows some some sharp maxima and minima at certain angles, which were found to depend upon the electron energy and hence upon the accelerating voltage. This pattern was similar to a wave diffraction pattern. Some typical results from these experiments are shown in the figure. Shown in the figure here. Davison and Germer found that angular peaks of scattered electrons could be explained as diffraction of electrons by atoms if the regular arrays of atoms in a nickel crystal are regarded as diffraction grating. So here you learn about quantum physics by quantum Kishan, quantum Farmer, quantum Krishak from Bharat. And I expect you will enjoy my lecture very nicely.